Okay, I think we can get started here. So everyone, I would like to introduce Dr. Poonam Khatri. She's a postdoctoral fellow at my lab, and she's also a visiting scholar with Forest Products Laboratory in Wisconsin, Madison. She got her PhD from Khatri Institute of Technology in India, and her master's and undergraduates from Hanover University. She does sustainability, environmental sustainability and life cycle assessment, and she has been doing it for a long time. She's kind of an expert on it. So today she's going to talk about carbon benefits of alternative utilization pathways for forest residues. Please go ahead.
Thank you. Great honor to be here. And to start with, carbon benefits of alternative utilization pathways for forest residues. So we try to focus only on the carbon aspect, though there are several others. So pardon me there, because we'll be focusing more on carbon. So why this focus on forest residues? Forest residues, they are unmerchantable, and they are derived mostly from the forest operations, logging, thinning, and restoration activities, include branches, tree tops, and small diameter trees mainly. And according to a US billion-ton study in 2024, US forests produce around 18.5 million tons of dry tons of logging residues and around 3.1 million dry tons from small diameter trees. So we have plenty of million dry tons of residues to use. And what they are, how they are managed currently is mostly pile burning and naturally left on site for natural decomposition. And it's obvious to see them that as an alternative source for renewable energy, but there have been several studies which says that logistics, economics, markets not available, or market demand for the use of those residues, and the scale of technologies. So there are several factors which act as a constraint. And but there are other studies which also say that around 65% of the residues still can be, if there is a technology, if there is a market, can be used. So given that assumption or that consideration, we are going to look at those alternative pathways. And okay. Hello. Give me a moment. So being pile burning is the most common management for forest residues. What are pile burns? These pile burns are created by hand or machines as a necessary treatment. Because there is so much residues lying on floor, we need to manage it to regrow the forest for next cycle and to prevent the wildfire risk. So we have to remove them. That's how they are burned in piles. And it has been a common practice since many, many years. And prescribed, these pile burning are managed with some fire plan. So it's a controlled burning. It can happen multiple times in a year and considered to be a relatively inexpensive practice. So that's why they have been used. But there are cons of this pile burning practice. The emissions, they are uncontrolled, and the particulate matter, because the combustion is not efficient. So those risk of air pollution and health risk is plenty, or it has been acknowledged widely. And also wherever these sites are burned, there is a soil heat damage. And the unaccounted costs of it leads to various unaccounted costs, which often excluded from the studies, but there are acknowledged risk of those pile burning. So we are looking at the greenhouse gas emissions in today's presentation, and what are the global warming impacts. So greenhouse gas emissions are termed as global warming impact when we convert them to kilogram CO2 equivalents. And when we look at that, they are measured in some long-term greenhouse gases. So greenhouse gases which stays for a longer persistent time in atmosphere, they are accounted for global warming impacts. But because these forest residues, the carbon in forest residues was thought to be carbon neutral as for the, according to IPCC, because they will be regrowing, or they are part of a cycle which is much shorter than fossil fuel carbon. So they are considered carbon neutral, but there is some methane emitted, and that says this is the 0.143 grams CO2 equivalents per kilograms of residue burned in piles. So that is like mandatory, but there are some other pollutants which are not long-lived and often excluded, but they also indicate toward the risk of pile burning, which are like carbon monoxide, black carbon, and if we include these short-term criteria pollutants as well, the global warming impact reaches to 730 grams per kilograms of residue being burned. So what we are saying here is that even if we consider as carbon neutral, there are global warming impacts. Even if we do not consider CO2 as a causing to global warming impact of pile burning, there are other impacts. So this in fact reinforces us to use or to look for alternative pathways to reduce these criteria pollutants, to reduce these other methane, biogenic methane. So moving beyond pile burning. So how do we move beyond pile burning? What are the options we have? So we can use those residues for generating energy in the form of electricity, briquettes. Briquettes can be burned for heating. Briquettes, if they are torrefied, they can be burned with coal for generating electricity. And they can also be converted to aviation fuel. So these are the energy uses. And there's small diameter trees or some usable or selected, if there's a technology, we can use them to make particle board. And we can even make mulch, just a simple grinding process. We can convert them to biochar. So there are different choices in energy and products. But how do we find a balance, or which choices are good for a particular site? So there are different options. First is availability of market. Like for woody biomass is currently, there is a market or technical feasibility to produce electricity from woody biomass. That is one option. Then processing near the site was also a consideration, low capital technologies. And then if we want to have higher economic returns at a larger scale, there are technologies like aviation fuel generation. And because burning emitted the carbon instantly, so we want to also have some options where that carbon can be stored for longer. For example, in particle board, making a wood product, making biochar, storing it in soil, or using it as a soil amendment, additional benefit. So considering all these choices, we looked at different options which fit all of them. So some options will fit just available market, some option will fit on higher economic value. So we'll see all of these options. And then how do we compare these alternatives when we are assessing them? So because they serve different functions. So briquette cannot be compared with biochar, or electricity cannot be compared with particle board. So which quantified function we should take as a comparison basis? So we took global warming impacts, and we conducted a cradle-to-grave life cycle assessment for global warming. And what we do there, we compare the impacts of combusting 1 kilograms of residues in pile, and using that 1 kg amount to produce that alternative. And in some cases, there was a benefit. So let's say we generate electricity, that electricity will be used somewhere, and it will be avoiding the same equivalent amount of electricity from grid. So that way we can account for some emissions being saved. So we'll see next that in some of the alternatives, we have this displacement benefit, but in some of them, we do not have a displacement benefit. Let's say we make particle board. So particle board maybe from residues will add to the supply of more wood, but there were no as such, non-fossil or non-wood product to replace, like biochar. Similarly, biochar, there is no one-to-one conversion with synthetic fertilizer, or there are so many indirect uncertainties factor. So the displacement benefit, I'm just saying that, was accounted for some of these options, not all of them. And we'll be talking about each of these alternatives one by one. But just to begin with each alternative, the the objective for each, like for each of the product which we alternative we are studying, we have these key objectives. First is to quantify the life cycle of global warming impact for that alternative, and then to compare it with pile burning. And if there is a displacement benefit, if it is avoiding a non-wood product or fossil waste equivalent product, there we were accounting for the displacement factor. And this displacement factor is nothing but greenhouse gas emissions of the non-wood product, subtracting the greenhouse gas emission of that wood alternative, and it is divided by the carbon stored in that woody residue-based product which we have. And for this, the life cycle assessment was the main methodology. And if life cycle assessment follows the methodology guided by ISO standards, so methodology is pretty standard, but it is flexible for the product or for the objective of our study. So life cycle assessment being conducted for a wood product will have a standard methodology designed for wood product, and will have a standard methodology designed for, let's say, a textile product or any other product. So methodology is standard and flexible both. That's what I'm saying. So for this study, we have different LCAs. So LCA of electricity generation and LCA of sustainable aviation fuel generation. So that's how we designed the methodological choices as per each of alternatives. And these 4 stages are the key steps of an LCA study, and each have different methodological choices involved, and that's how each study is limited in a way or bind by the choices that go inside that study. Since we are considering only the carbon benefits, so we have included the only global warming impact, but this methodology applies for several other impact assessment methods, impact categories. And the methodological choices, if we see which is common to all of these alternatives we are going to see, methodological choices. The goal was GHG emission profile for each alternative. So that's what cradle-to-grave life cycle, GHG emission profile from cradle to grave, and the functional units or the quantified function was different. Like say for aviation fuel was 1 megajoule of SAF. For biochar, it was 1 kilograms of biochar. For particle board, it was 1 meter cube of particle board. So that's how they were different. And then they were re-estimated for 1 kilograms of or 1 ton of forest residues as well. So they have we have 2 estimations for each unit function and for each unit residue used for this versus that. That's all the residues. And the global warming impacts for each greenhouse gases included, they were accounted for a 100-year time horizon. What we see in this table is the global warming potential of these long-lived greenhouse gases. So these long-lived greenhouse gases has a lifespan in which once they are emitted from the process, that's long they last in the atmosphere before they are broken down by a chemical reaction or naturally they get reabsorbed. So that's how long they stay. And this last column is the global warming potential they cause because of the radiative efficiency or how much heat they absorb or how much warming they cause. So moving on to our first alternative pathway, which was electricity generation. And this slide defines the scope of this LCA for electricity generation from forest residues. So we have forest harvesting, giving us roundwood and these forest residues. Because the use of these residues, either we use them or we do not use them, will not affect the operations of forest harvesting. So our system boundary was excluding the upstream forest management. So forest residues which were used for electricity generation were assumed to have no upstream burden coming with it. So they were assumed burden-free because all the impacts were going with the roundwood, which is used for making wood products, lumber, or so other products. And the function unit for this system was 1 kilowatt-hour electricity. And the residues were assumed to be air-dried before they are recovered and collected. They were transported to a 100-kilometer distance for the power plant facility. And it was a 20 megawatt power plant, having a conventional steam power turbine working on a 25% efficiency. And the electricity generated for one 1 kg residue was around 0.882 kilowatt hours. And once this electricity is generated, it was compared with the grid electricity. So that substituted electricity was assumed to have 2022 national E-grade emission factors, which was 375 grams per kilowatt hours. So for the impacts, we use this as a reference to estimate the displacement benefit. So to see the benefits, so the electricity generated was 37 grams or 0.037 kilograms kg CO2 equivalent per unit of residue-based electricity. And the contribution of these key life stages was around 58% from electricity generation and around 31% from the transportation. So that also tells us the logistics were important. If the plant was situated much further, or where the location of plant was, that could contribute to the higher or lower global warming impacts. And the recovery of residue was least in that. But this is for 1 kilowatt hour electricity. So if we compare that with the percent reductions, how much reductions it has when we compare for pile burning or when we compare with grid electricity. So the percent reductions against a 1 kg residue used for electricity versus 1 kg used in pile burning was 79%. Emissions were 79% lower, and it were around 91% lower than grid electricity. So these were the reductions we could see. And the formula, which I showed in 2 slides before, using that, the displacement factor achieved was 0.164. And a positive displacement factor indicates that forest generated electricity has it displaces more emissions than it generates during the process. So that positive indicates that there is a benefit of replacing or using those residues for. And since our fossil electricity grid still relies on fossil fuels, around 60% of the grid electricity is using fossil fuels. So there is plenty of scope using the residues for electricity, because that has been technically feasible and already in use technology. So that pathway we used as a first choice. And the second choice we had was briquettes. And briquettes were used for 2 purposes in our study. One was burned in a wood stove for heating, and one was modifying the briquette further and using it along with the coal in a power plant to generate electricity. So we have 2 briquette LCAs. So one was with non-torrefied briquettes produced and used, and this was the system boundary for that. And the manufacturing for those briquettes were assumed to be near the site of the piles. So the transportation of residue after recovery is only nearly 19 kilometers. And these inventories, or the transportation distances or the assumptions about these data, they come from Waste to Wisdom and another LCA study, which was completed by USDA. So there's been a field study which was implemented for making these briquettes. So from where we took this data. So it's not like just only the assumptions. And then it was transported to a 90-kilometer distance to produce, to be burnt in a wood stove. And the wood stove was burning around 72% efficiency. And there it was assumed to substitute propane, which is supposed to be most commonly used fuel for heating. And the emissions of propane, 1 megajoule propane was 63 grams or 0.063 kilograms of kg CO2 equivalents per megajoule of propane. So we compared this with 1 megajoule of briquettes from wood residues. For the torrefied briquettes, the briquettes are given a heat treatment to increase their energy density. They burn better, our combustion is better. And there they are assumed to be burning with in combination with coal in a power plant. So they will be reducing a certain amount of coal for the equivalent energy. And the manufacturing is supposed to happen near the same location, near site, around 19-kilometer distance. And the distribution for the use was farther, around 200 kilometers, 211 to be precise. And there it's is substitute coal. And the impacts of 1 megajoule coal were around 309 grams per megajoule.
Can you tell the difference between briquette and pellets?
Yes, yes, I can talk about them. So briquettes use a lower quality biomass. So normally these woody residues are more dirty and not very much clean. They are so briquetting can allow use of less cleaner fuel. Pellet require more clean and more consistent fuel. So that's why we instead of using pellet, which was more common choice, we used briquette as a feasible option for the residues, like more realistic. So for the non-torrefied briquettes, we saw that for 1 megajoule, the reduction or 1 kilograms, for 1 megajoule, we see in the figure, we see the contribution of life stages. Of course, the manufacturing has more contribution because everything has to be taken to the forest site. So it was a small scale operation near the forest site. So whatever equipment or briquetter we were using, it has to be transported. The fuel used in the briquetters, it was a decentralized option. So that's why manufacturing has more emissions, obviously. But when we compare that 1 kilogram of residue used for making briquette versus pile burning, there were still 28% better global warming impact. And when we compare with the propane, the impacts were 87% better or reduced for 1 megajoule. And the displacement factor was around 0.38, still a positive displacement factor. For the torrefied briquette, because the coal is more dirtier fuel than propane, we saw better displacement factor. If you see directly at the bottom, almost 1. So because coal has itself more global warming impact, so the displacement of coal led to better global warm or better displacement factor. So the percent reduction was 94% for coal, but we saw that manufacturing stage has higher impact. So that will be there. And the next alternative which we tested was sustainable aviation fuel. It is based on a gasification-based Fischer-Tropsch mechanism. And the yield of SAF produced was around 13%. And having a heating value of around 43 megajoules per kg. The goal of this LCA was global warming impact for cradle-to-grave life stages of producing. So we are not only producing, we are including the use of the SAF in burning along with the jet fuel. And the system boundary is indicated within this green dotted lines starting from residue recovery to a SAF combusted in an aircraft engine. And the SAF production facility was assumed to be a location of 160 kilometers from a forest collection site. And the transportation for use location was farther, around 600 kilometers. That also coming from another study. The data collected was like not just an assumption, that's what I'm indicating. And it is supposed to substitute the jet fuel. And because once the SAF is generated, the properties of SAF and irrespective of the feedstock, once the SAF is generated, the properties are similar. So they are supposed to be burning in a similar fashion in the jet engine at the end. And this global warming impact of the substituted conventional jet fuel were 84 grams per megajoule. And the impacts of SAF were around 26 grams or 0.026 kilograms per megajoule. And we saw that the contribution of life stages shows production stage has more impacts. But the transportation and distribution, if we add 7 and 5%, so that also include nearly 12% impact. So that indicate the importance of logistics. That's what I'm highlighting. And if we compare the reductions with the global warming impacts of pile burning, so 1 kilograms used for pile burning and 1 kilogram used versus for SAF production, there was a 15% decline because there's more impact in transportation and production. So the percent reduction are lesser when we are having longer travel, longer or larger scale operations. That's why we saw lesser decline in the global warming impact, but still better than pile burning. That's what. And we are not only reducing these greenhouse gases, we are also reducing the criteria pollutants when we say alternative use of residues. And compared to the conventional jet fuel, the impacts were 70% lower when we used forest residues for SAF. And because there was an equivalent non-wood or fossil-based equivalent, so we could estimate the displacement factor. So what we saw is around 0.15 displacement factor. And as I said before, a positive displacement factor indicates better global warming impact, better say the word is not coming, but it indicates that it displaces more emission than it generates during the generation. So generating SAF from residues was not impact free, but it was lesser than jet fuel, conventional jet fuel. So far we have seen only the energy alternatives, and in the energy alternatives we had a non-wood or fossil-based equivalent, so we could estimate those displacement factor at the bottom. But next we will see the products, and when we use the residues for product, because there are no maybe established market or no right substitute, we do not have a displacement factor estimated. So let's say we use particle board. So the particle board has several end uses, which was beyond the scope and is not standardized. So even if we pick one, let's say plaster board or any other board, so that would not have been a right displacement factor estimation. So we skipped the estimation of displacement benefit. But to produce particle board from forest residues can be justified because those particle board will keep that carbon stored for longer year until they are in use, which is normally beyond 50 years. We have assumed 75 years. And the representative data, LCI data, I mean, because we had more data on manufacturing of particle board, so there was two system boundaries we decided. So we estimated the global warming impact only until manufacturing. And then for the downstream stages, we applied our own assumption that it is distributed to a 200-kilometer distance. It is used for this purpose, and then it's sent to a landfill at the end of the life. So that's why the cradle-to-grave impacts were more based on our assumption, our own. But the cradle-to-gate impacts were more representative. And this table shows the properties were similar to a conventional particle board if we made, and it was 663 kilograms per meter cube of particle board. So more residues goes in making of a particle board. And if we see the contribution of life stages up to the manufacturing stage, which was cradle to gate, we saw that for 1 meter cube, it was 181 kilograms per CO2 equivalents per meter cube. But if we estimate that for 1 kg residue, it came down, it was 0.28. This was done to compare it for 1 kg residue being pile burned. And for cradle to grave, we see that as the system boundary is expanding, the impacts were higher, 243 kilograms CO2 equivalents for 1 meter cube, and for 1 kg, 0.386 or 386. So what we see here, you can say for 1 kg residue. So this was the number which we were comparing against pile burning, 0.288 and 0.386, because this is for 1 kg. And in the these bars we are seeing on left side is cradle to gate contribution of life stages in cradle to gate global warming impact. And we see that manufacturing is accounting for, of course, the highest. And second was the other raw materials which goes in the manufacturing, not because the raw material for manufacturing of particle board is not just forest residue. There were other resins or adhesives being used. And for cradle to grave also, we saw that because there are other life stages included, the contribution of manufacturing stage is going down to 54%, but there are other stages contributing significantly. But yes, like I mentioned before, no avoided emission benefits, and it can be justified that it will be adding to the wood availability. So there will be additional supply of wood if we use for forest residues-based particle board. And the next alternative which we are saying today is biochar. For biochar production, we use those residues for burning in a mobile air curtain burner, which was also producing near the forest landing site. So they are mobile pyrolysis units. So now not sending it to further to a larger scale plant, but a near site pyrolysis happening in a mobile air contained burner device. And in that pyrolysis, the carbon or the biochar produced has 83% carbon in biochar. So that's what pyrolysis is doing, with fixing the carbon. So the forest residue we assumed has 50% carbon. After the pyrolysis, it's 83% carbon. And in that 83% carbon, it is said to be having two fractions. Like that pool of 83% can be divided into a labile pool and a recalcitrant pool. So labile pool decomposes faster, and recalcitrant pool is like it resists to decomposition. So even if we apply it on soil, it decomposes really, really slowly, or in fact, it does not decay or for more than 100 years. So it decays, but it's extremely slow. So the decomposition rate you can see for labile pool is per day, and for recalcitrant pool is per year. So all the labile carbon decomposes, assumed to be decomposed in first year of application. We apply it as a soil amendment. And recalcitrant pool we assumed, because our horizon of assessment was 100 years, so we assumed it's emitted but very less. So most of it, around more than 90%, was still there after the 100-year estimation. And this dotted line just indicating the boundary. So we have not included the displacement benefits because biochar we did not have a one-to-one substitution. Find out that biochar will replace this fertilizer by this ratio because of the uncertainty in indirect effects. So we just assumed the benefits of carbon not emitted. So the carbon being stored in soil. And that's what we are seeing here. The percentages looks very high, but they're compensating to a negative 2.03 kg CO2 equivalent per kg. So per kg biochar, we have negative 2 kg CO2 equivalents largely because of the carbon being stored. So that is compensating for the emissions. And if we convert it to 1 kilogram CO2, the impact was negative 0.35. So this is the number which we will be comparing, 0.35, we'll compare with the pile burning. So if 1 kg pile burn versus if 1 kg is used for biochar is negative 0.35. And climate benefits even without the substitution assumed. And of course, we can say that this is conditional given these assumptions, because we have assumed a near site operation, we have assumed a certain processing condition. So if the biochar is being produced at a 500-kilometer facility distance and the facility scale was different, so these benefits probably will change. But we are seeing the benefits being compensated because of the carbon being stored. So that is a big advantage of producing biochar from forest residues. And the last application which we assumed was even a very simple technology, just grinding the forest residues to mulch, make them usable, and spread it on the landscape. So we can spread it on a previously burnt slash pile sites. So we can use it near the where the slash piles are. We don't even have to transport it much further. And mulch is similar to biochar. It also has some carbon in it. And that carbon has different, like the recalcitrant and labile pool. It has more labile pool. The recalcitrant pool, which we were saying it will decay slowly, was only nearly 10%. The rest is labile. So it will have more emissions. But because of this 10% recalcitrant and we are not burning it, it also showed benefits. So we saw that even if it's a simple technology, because there were not much of a technical process, only simple grinding. So the impacts of the units inputs used in making a mulch were lesser. So impacts were negative 0.31 for 1 kg of mulch and negative 0.124 for 1 kg of residue used making mulch. And this negative global warming impact indicates that soil carbon storage outweighs even for this producing mulch. So that is said to be more simple use of residue rather than pile burning. if we have specific, locations identified. So these were the 6 applications which we studied, and because so far they were studied differently or individually, if we see them together, on the left you see, so these impacts are cradle to grave global warming impact for 1 kg. So they are re-estimated for just 1 kg. That's how they came on one single scale, even if they have different functions. So for 1 kg, for different uses, these are the impacts. And we saw that biochar and mulch are showing negative global warming impact. And other applications, except particle board, all other applications were showing better global warming impact compared to just pile burning. And particle board also, we could justify that it will be storing the carbon for longer time. So if we are not accounting that storage benefit, but if that was accounted, and that will also be better, prove better in long term. And like I said, for these selected ones in the dotted boundary were energy uses of residues. And for these energy uses, we estimated the avoided emissions. So we did that extra factor or displacement factor estimation for these 4, but not the other ones. And if we see all of them in a table, we see on the left side is the list of all the uses, so residue used for pile burning versus the others. And in the second column, we see the impacts per kg residue. So here the units are not individual 1 kilowatt hour or 1 megajoule. They are just kg CO2 equivalents per kg residue used in these applications. And then percent difference with respect to pile burning. And in the last column, we see displacement factor estimated only for the selected ones. So if we want to, choose, or if we want to rank them, how will we do that? We saw the negative global warming impact. So we tend to rank biochar and mulch as the first choice. If they are being produced near the site, or at if they are produced at significant scale to have sufficient quantity of residue reduced. So we want to reduce that amount of residue which are pile burned. And we do not have the scale of technologies that all of the residue can be used. So as much scale we can provide, the biochar and mulch seems to be first choice. And then second was electricity, which is already being tested or being used for electricity generation. And then number 3 was using those residues for making briquettes for heating. And the SAF was 4th because it will have higher economic return. Many airlines are aiming at reducing their global warming impacts by, or they are aiming to substitute their fuel demand by 10% with the SAF. So the SAF can come from agriculture feedstock and forestry residue feedstocks. So that's where these residues can supply those feedstock for SAF generation. But it requires larger investment or larger scale operations. So that may be a long-term strategy, but for near term, we have ranked biochar and mulch as first, and then particle board at the last. So producing biochar and mulch, of course, looks more readily deployable strategy and as compared to the other ones. So that's how we rank. And so forest residues, to be concluded, they represent a severely underutilized resource, and we have to adopt some diversified strategies to use them, and different options can suit different conditions in different forests. So that's why we have to have a mix of residue utilization alternatives. And first, our feasible choice would be readily deployable near forest site, low capital technologies where those biochar, mulch, or briquettes can fit. And in the mainstream options, which are already in use in many regions, their electricity is available. Electricity use is a feasible option, and then more capital intensive and future oriented options offer long-term potential where the SAF and particle board kind of products will come. That was the end of the key references which I cited during the collection of the inventory data, key references. Thank you.
Questions?
Yes.
I actually have two questions.
Yes, please.
Okay.
Yes.
First of all, when you're talking about forest residue, is only like a logging residue, or like if it's only wood chips, or it does include like barks, branches, and others?
Yes, so all of them. We are talking about the branches, tree tops, small diameter trees, whichever is not taken by the sawmills. The residues left on site considered to be unmerchantable, like no commercial value.
And can they use all of it to make sap?
No.
That
Of
has
course,
to-
there has to be technical feasibility, and then how much can be collected. So yes, so there first will be recovery and collection. So first recovery and collection is mandatory, and then there will be a screening probably to, if it is being used for making briquette, we don't need screening. But if we are using it for higher energy application, then we need that screening. Yeah.
What I'm really surprised about is particle boards, because
Mhm.
when you're making particle boards, for instance, using them for cabins, they're gonna
Yes.
stay, like you're storing that cabin for
Years.
at least 20 years.
Yes.
Did you conduct into your calculations, like like if you burn them, you immediately release the CO2 to the air versus storing them
it, yes.
for 20
Yes.
years?
So that will be like dynamic LCA if we include the delayed release of carbon dioxide. So the time factor we have not accounted in this study, but we have accounted the disposal of, at the end, what will be the disposal of emissions because of the disposal. Yeah, but this is just one study, and it came out of another study. The main project which I was handling was harvested wood products, dynamic LCA actually. There we have forest being converted to primary products, to timber use products, and then end uses. So end uses are going, some end uses will last more than 100 years, some products will last only 10-15 years. So based on when they are going out of use at that time, so the emission timing will be different. So manufacturing, even if happening at one time, the emission at the end will happen at staggered time scale. So I've accounted those in assessment of harvested wood products. But because of the residues, this LCA, we did not include the time component. Yes.
Questions?
Yes, please.
So what's the major reason why you didn't include a time component and do a more dynamic LCA in this case? But it seems like with the carbon cycle, the residence time is going to be really critical to the actual climate impacts.
Yes, for particle board, it would have make more sense, but for other alternatives, it was not that important, because using for residue used for electricity, residue used for briquettes. So we assume the briquettes are used within first year.
So it's
So
almost instantaneous.
yes, for other,
Biochar would be an exception too.
yes,
right?
biochar will be an exception, and we have accounted that for biochar actually, but not for the particle board, because we assume that it is going to be remain in the product, let's say cabinet or any other product of particle board. It will be staying as it is. So once we have manufactured the product, it will stay as it is for 20 years or 50 years. So the same amount of carbon instead of released late. So the quantity we have not lost. Instead, we have not taken the credit of delay. So we are being conservative in a way. Yeah, because if we had taken the time component, then it would have been even lower, the impacts. So that's what we have seen traditional and dynamic LCA in other wood product LCA study I did. Yeah. We found for other wood product study, we found around 60% reduction for the other timber lumber products. Yeah. That study we did for California.
Please, the room. Thought there are some questions in Zoom.
Okay.
So, so there's a question from Hanover. Do you want to ask yourself or should I read it? Okay, Hanover is asking, is the biomass heating efficiency included in your comparison analysis, especially when you compare and calculate the displacement factor of biomass generated electricity via coal-based electricity.
Yes, we have included that.
You have included.
Yes.
So,
If you want to know, the wood briquettes being used for power generation were assumed to have 25% efficiency, whereas the coal being used for electricity generation was around 35%, we assumed.
so another question from Manasseh is, what was the impact of the woody biomass on the performance of the particle boards? I think he's asking a bit more.
Performance. So we assume that properties of the particle board made from forest residues are same. So that's what I was showing in that presentation slide. Yes. Yeah. So the properties were assumed to be same. In fact, there is no LCA as such conducting on particle board made from forest residues. So we assume the material and energy consumed in making the particle board were same as making a traditional particle board. So we assume the same, properties.
What was the conversion factor? Because you have to screen and you have to get rid of a lot of stuff.
So we have assumed some losses, or we assumed around 663 kilograms per meter cube. And I don't have the number on top of my head, but we have accounted for that losses. Yes.
So I have a question.
Yes.
Thank you for a great presentation. And so your results indicate that the biochar can be pretty promising.
Biochar can be?
Is one of the best choices.
Yes, one of them.
Right?
Yes.
And is there enough market that you can use biochar for like any applications, like agriculture or something like that?
Yes.
I just
This market is not established. I think people in this field know that established market is not, but it is growing at a much faster rate than it was years before, because all of these applications, probably except SAF, they have been there. Like people have been talking about individual application, residue-based electricity, residue-based biochar. We just try to bring them in one basket together. How do we see one versus another? That was one objective. And instead of, because those large scale operations were not that many, but transporting those residues, so to biochar plant 500 kilometers is, will be difficult because the market is not there. But that's why Forest Service has made a, char boss, they call it, the device they have named char boss is a mobile pyrolysis unit called air curtain burner. So they transport that device and they burn it, they generate biochar, they pelletize it and then send it. So it's better than pile burning. Yeah. And in a way, all these applications, let's say even mulch, it is reducing the residue to be burned. So probably will not be able to take care of all the residues which are pile burned, but will reduce the amount of residue which require burning.
Did you look at the PM25 and PM10? I think that's where you would see the biggest reduction.
Yes.
To pile burn.
Yes, we because they were short-term criteria pollutants. They lived shorter. Once they are emitted, they have more potency of health risk they cause. So we just say that we are avoiding the burning. So the whatever was emitted during burning is not emitted now. So direct comparison was not done, because for direct comparison, we included only the long-lived greenhouse gases, and long-lived greenhouse gases meant carbon dioxide, methane, and nitrous oxide. So we included only those three.
So Hamdi has a hands up. Go ahead.
Can you guys hear me?
No, I can't hear.
Can you hear me? Sorry.
Where is the mic? Hongmei, I cannot hear you properly.
Okay. Is it? But anyway, can you hear me if I ask a
yes,
question?
if you can try speak, I can try. Yeah,
louder. Okay. So based on what you just said, answering that question for biochar, I'm thinking that basically you are comparing basically the biochar carbon storage in the biochar versus to compare
Yes.
the
We are
blast.
talking about biochar storage. That's what you said?
Yeah, basically what I'm seeing that your result showing is the impact of the storage, biogenic carbon stored in the biochar to compare with the pile burning, which exactly just emitted immediately the
Yes.
biogenic carbon. So it's a two concept you're comparing, because biochar has, if we're talking about the LCE analysis, one is your cradle to grave and the other is cradle to gate, because the biochar carbon has not been released or has not been hitting their end of life. Is that correct?
Yes. So we are assuming that the end of life of those carbon, if for the sake of audience, what Hongmei is saying is that the carbon in biochar is there in soil. So it has not met its end of life. And what we are saying is that carbon is recalcitrant or resistance to it has more resistance to decomposition. So it will stay more than 100 years, and our time horizon was 100 years. So studies have shown that it will decay much, much slowly. So we are assuming that both that horizon, that cradle to grave life cycle is ended. Like we have applied it somewhere. It's not reusable now.
So that biochar you're talking is gonna be applied in the soil. That's
Yes.
the application. But yes, it is can be confused to people that was trying to utilize the biochar for other applications. When they hit their end of life, it can be burned again or decomposed in a faster way rather than the soil amendment.
Yeah. So we have used only one application of biochar. Of course, biochar can be again burned for other application. Biochar, there are studies which says biochar used in making concrete, biochar used in making, modified concrete or modified other, products. Biochar used for water treatment, biochar used for air purification. So those applications will have a certain different, life stages than what we assumed here. So what we have assumed is more conventional, like transporting those biochar to any site and applying it similar to fertilizer. So the application of biochar has similar impacts like applying a fertilizer on soil. And after the application, we are not assuming that it has substituted a fertilizer. It has just added nutrient to the soil. So we have not included the displacement of fertilizer or synthetic chemicals.
Other questions?
Was that answering your question?
Yes.
Okay.
Thank you.
Yes.
So you talked about using biochar for generating electricity. What happens if you use it for producing electricity and heat? Does that have any effect, or would it have similar kind of work?
So if it is being burned, how it is burned, that will depend on, because burning a direct residues versus burning a biochar will be different. The combustion efficiency will be different. And in fact, the residues were burned in an open environment, and in the power plant, there will be more controlled environment burning, more like pollution control devices will be there. Certainly the emission benefits are there compared to bio burning, but emissions will be instantaneous. So
I was saying, instead of just producing electricity, if you produce combined heat and power.
Yes, so that can be an option, definitely. Combined heat and power plant. Yeah.
But will that make much difference, or do you think it would be pretty similar to just making electricity? That's what I want.
That will be more beneficial, but depends on where it is. Like if it is integrated within an industry, so that industry is using the heat generated, and then electricity is additional. So that electricity they can sell to the grid or use it for their own on-site requirement. Because there are several like sawmills. They have combined heat and power plants on site, and they use their mill residues either to produce just heat, so they don't produce any electricity. They just use for their heating requirements, and some produce heat and electricity both. but of course, whenever it is generating heat and power, it will be substituting some heating fuel, whether it was coal or natural gas. So that displacement, it will take the benefit if it is using for, heat.
If not, then I have one question. So you talked about sustainable aviation fuel, and it has the least, impact compared to other ones.
Okay.
Can you explain why? What are the? I want to know the assumptions, because are we using? Is it because of the transportation, the process technology,
Yes,
the energy which is coming from grid?
yes,
Yeah.
yes.
So can you explain that why it has the least impact? Because I would have assumed that it would have a better impact compared to.
So if we can share the screen so that other can also see. So that's what you are pointing to, like, because the reduction as compared to pile burning was least. That is because of the operations of producing these aviation fuel and the longer transportation distances. Because when we compared it with the conventional jet fuel, like 1 megajoule versus 1 megajoule of SAF versus conventional jet fuel, it was 70% reduction compared to the jet fuel. These reductions are compared to the pile burning only.
Oh, okay.
Yeah. So because those alternatives were different, if you see the so compared to jet fuel, the reductions were 70%. When we see this graph on right hand side, so there is no like as single scale. For pile burning, this comparison is 1 kg residue used for SAF and 1 kg residue burnt. But the lower bar for jet fuel is 1 megajoule. So 1 megajoule of jet fuel versus 1 megajoule of SAF. So the global warming impacts are compared with jet fuel are 70% reduced in SAF.
So SAF production, most of the emissions is coming from production, even 77% of
Yes.
that, it's not
Yes.
transportation and recovery. So is the technology. So if we
Technology.
improve the technology, we can
Yes.
reduce.
Yes, and there is more incentive for SAF production because of the voluntary targets these airlines has set. They have aimed to reduce their or they have aimed to replace their fuel 10% with the SAF. The fuel can become from agriculture feedstock or forest feedstock. So if we have a supply of forestry residues for those facilities producing SAF, that could be an incentive. So electricity and SAF production has more policy incentives. Like electricity from forest residues will have incentives and SAF will have some policy incentives. So that's why we included SAF as an alternative. Okay. Hongmei has a hand raised.
Yeah.
Sorry. Quick question on this one, especially for this one jet fuel conversion use the biomass residue. Did you include the efficiencies in the whole, conversion chain?
Yes, Hongmei. We included the conversion of like from residue recovery, like how much will be the recovery conversion. It's not like top of my head, but we included that because it required screening of the residues. Not everything will go for SAF generation.
Yeah, what I'm thinking is mostly like a heating efficiency, because biomass or wood has a very low heating efficiency as compared to coal or fossil-based energy.
Yes, we have included that also.
Okay, thanks.
Yes. Yeah.
One more quick question. So
Yeah.
is this, have you published this? Can we cite you?
Yes, we have published this paper. I forgot to keep it. It was there, but yeah, we have published this study in biomass and bioenergy just last year. And it received good review response, that I can say. Yeah.
We are at the clock, so thank you everyone for staying. Who is hungry?